Okay, thank you. So, remember last time we discussed the construction of mirrors for general hypersurfaces in C to the n or in a toric variety, which gave us mirrors some Landau-Ginzburg models where the total space Y is a toric variety determined combinatorially from a tropical degeneration of H. W0 was a particular monomial, which is there, gives you the whole mirror for a hypersurface in C star to the n. And then when you go into a toric variety, this gives you additional terms. And I started explaining how we can compare the derived category of coherent sheaves of H with some fiber-wise wrapped Fukaya category whose objects are Lagrangians that are monomially admissible for W0 and the terms in WV and some extra ones that you make up if needed, if this is not sufficient to get control in all directions at infinity. So, and this is something that I've been trying to work with Mohammed Abu Zaid. Okay, so so the example that I ended with last time was the case of a pair of pants, mirror of a pair of pants, viewed as the hypersurface 1 plus x1 plus x2 equals 0 in C star squared. The mirror in that case is C cubed with minus z1, z2, z3. And I explained last time how if we look at the projection under W0, so the central fiber is the union of three C squares. The other fibers look like C star squares. And if we take inside C star squared the Lagrangian little L0 inside the reference fiber, and then we parallel transport it along the U-shaped arc. So we'll call that cup L0. There's a name for this operation. Then I end up with a Lagrangian that has, an admissible Lagrangian that has two legs over radial paths in the base. And in each leg you see something that differs slightly from L0 by a little bit of monodromy. But then when you start computing, so in this example, the wrapped Fleur cohomology, maybe the, because I just defined it to be the endomorphisms of L0, end up being, as a chain complex, you get, I'm not going to draw the picture because I'm going to change this to compactify from C star squared to V very soon. But remember, in each fiber, I can still draw the picture in the base. In the base, when we perturb L0 by this flow, I denoted the perturbed version. This is probably not visible, right? So let's try a different color. Not really much better, anyway. So this was going to be the perturbed Lagrangian L0T. And in this version of the story, I was going to do fiber-wise wrapping, so that I would end up with two copies of the wrapped Fleur complex of R plus squared with itself at each of these intersections. So, which is Laurent polynomials in two variables. And the differential, which counts holomorphic sections over this region. ended up being exactly multiplication by f, the defining equation of a pair of pants. So that we ended up with the rank of functions of H. Okay, and the same calculation works for all hypersurfaces in C star to the n. So now, and so this leads to homological mirror symmetry for the pair of pants, modulo a statement about L0 generating, which here works fine, and Zach tells me that I should probably not be less cautious, but anyway. Okay, so now if I compactify this, let me stay here for a bit longer. So if I compactify now to a toric variety, so let's compactify this to be inside CP2. Okay, so I will instead think of this as a line in P2. Then I need to add terms to my superpotential. 3 terms, one for each compactification divisor. And let's see what I did for a problem. But okay. So now the effect of these extra terms of the superpotential is that the fibers, right, so the fibers of W0 are now, well, they're still C star squared, but if I now look at the restriction of this extra term W sub V, that is going to be T times Z1 plus Z2 plus Z3, which you can rewrite as minus constant over Z1, Z2, and up to some fiddling with the constants, you recognize here the mirror of CP2. Right? C star squared with Z1 plus Z2 plus constant over Z1, Z2. So in general, this is a general phenomenon. The fibers of W0 will end up being the mirror to the toric variety V in which we are now working. And so now the way that this modifies our construction of a Fukaya category is that we no longer wrap fiber-wise. And of course, we impose admissibility with respect to this potential, but I was already doing that for purely technical reasons before anyway. So, okay, so we don't wrap fiber-wise, which means we just do a small perturbation at this point. Now, if I try to calculate the endomorphisms of L0, I will find the cohomology of, the X from O to itself on P1 inside P2, which is interesting but not very exciting. There's only constant functions. So it's more interesting if I actually look at Lagrangians that are mirror to other line bundles. So now I can start from, I will call L sub k, inside, again, the reference fiber, which is mirror to O of k under HMS for P2. So what does that look like? This is a Lagrangian section of the log map from C star squared to R squared, which is admissible. And the arguments of Zi twist by 2 pi k across some dividing line that looks exactly like the picture in the central fiber. I'll return to this a little bit. So for example, as you go through here, the argument of Z1 twists by 2 pi k, and argument of Z2 remains everywhere equal to 0 as needed to satisfy admissibility. If you want to know, there's these admissibility conditions that in each of the 3 possible directions at infinity, one of the variables is constrained to be real positive, but the other one is free to twist, and you use that freedom to twist between the regions where all the variables are constrained. I mean, in some sense, this is a slightly exploded version of the Lagrangians that Mohammed introduced in his thesis now 15 years ago. And so now you can calculate in the fiber-wise Fukaya category the Floer complexes, or the Helms, whatever you want to say, between L0 and Lk, and you find that this matches the cohomology of O of k in P2. So if k is positive, this is just homogeneous polynomials of degree 3 in, of degree k in 3 variables, x0, x1, x2. So now let's return to the picture here. And let's say that I want to calculate the Helms from L0 to Lk, then I will do the same construction as before, except I will parallel transport L0 along a U shape for one of my Lagrangians, and Lk along a U shape for the other Lagrangian. Okay. So L0 still looks like before. But Lk now twists, I don't know how to draw that properly, so I will just draw something like that. It twists by a finite amount of twisting that will have intersections with L0 equal, the set of intersections forms the basis of monomials of degree k on P2. Okay, so I will now expect, just erase the calculation here, and redo it. Oh, I think I know what's happening. I will not erase here, and then I will fix the problem. I understand the problem. Check. This one erases. Yes. Okay, so I will continue there instead. So if I look at Helms from L0 to Lk, I have these two places where things intersect with the origin in between. Okay. And so in here, we see the intersections between little L0 and little Lk. Now here we see something that's almost the same, but with one warning sign, which is that the monodromy around 0 is going to twist my Lagrangians by a small amount. And in fact, it's exactly a shear of the same kind as the twist that I used to get from L0 to Lk. It's a shear in the argument direction over the log map. Where argument Z1 shears by 2 pi across this, and same for the others symmetrically. So in fact, this is exactly what would take L0 to L1, and more generally Lk to Lk plus 1, and so on. And so what you see here is in fact the intersections of L0 with Lk minus 1. The more correct statement, because we are halfway around from the origin, is in fact this would be like L1 half and Lk minus 1 half, but it's easier to kind of straighten things and not bend your mind. Bend the picture instead. So what this now looks like is a copy of this one, L0 with Lk minus 1 in degree minus 1, plus a copy of L0 Lk over here, and a connecting differential, which is the same as before, because really it doesn't matter what we are doing at infinity for that. So this is again multiplication by, I used to call that 1 plus x1 plus x2, but now that I'm working in homogeneous coordinates, I will write x0 plus x1 plus x2. Remember, this one looks like cohomology of O of k minus 1 on P2. This one looks like cohomology of O of k on P2. And taking the cone of this, we end up with indeed something that's like the cohomology of the restriction to P1 of O of k. Okay, this is just a very complicated way of recovering degree k polynomials on a linear CP1, now embedded inside a CP2. And so using this construction, this works just the same for line bundles, mirrors of line bundles restricted from the ambient variety. Okay, so similarly for mirrors of line bundles on V restricted to H. And so this tells me, in fact, what I should be doing if I want to think about this more systematically. So now it's time to kind of talk about functors. But first, time to figure out if I can actually erase these ones. Yes, this one makes it. So the claim is that there are functors relating the Fukaya categories of the fiber-wise category of an Lagrangian small model and the category of the fiber, which is marked in my case just C star to the end, we can call it F for fiber. This is the fiber of double to zero, and still equipped with the extra terms in the potential coming from the toric parallelity. Okay? So the most obvious one, because we've just seen it, is this cup functor, which traces its origins, I think, to maybe all of in the prehistory of this kind of mirror symmetry. So this is sometimes called the Auroux cup functor. So what this one does is just parallel transport the Lagrangian from the fiber along a U shape. It's the one we've already encountered. Okay. Then there's a functor in the opposite direction, which is usually called cap. Okay. Cap L is respect to the ends at infinity. So you want to know basically what are the ends of a given Lagrangian. Okay, so now if you were in the world of like Lefschetz symbols or things like that from Lefschetz fibrations and this familiar setup, where Lagrangians fiber over a single arc with one end ending at some critical value, then cap would be exactly the vanishing cycle that you're transporting in the fiber. In this case here, my Lagrangians under consideration have actually two ends. So I end up with two objects of the category of a fiber at infinity. But I also should end up with a connecting map between them, which is exactly counting holomorphic sections between them. Okay? So in fact, this actually lands not necessarily in the category of a fiber, but in twisted complexes. Okay? And so this is like the ends of L at infinity, plus a connecting map which counts sections, counts holomorphic sections between the legs. Okay. And then there's something else we can think about, which is the monodromy around the origin, which acts on the Fukaya category of the fiber. Okay. And then there's one more piece of data. So now it's time to test my theory. So this is why it did not erase. Okay. This is why it did not erase. Okay. So there's S, which is a natural transformation, which for today at least, I want to think of it as going from the inverse of a monodromy to identity functor on the category of a fiber. Okay? And there's other versions that go from identity to mu, and which one you get depends on your convention for the cup functor, which side you go on. But I think this one works properly. So this natural transformation finds its roots in the side of a very long time ago. So what it does is, let's say that I have a Lagrangian in the fiber, okay, and let's transport it along. I could just do it along the U shape, but for the sake of making it more visible, So I take a Lagrangian L in the fiber, I transport it clockwise around the central fiber, end up at the inverse image under the monodromy, and then I want to count holomorphic sections. And this gives me a term S0 sub L in the Floer complex or Hom space of mu inverse L with L. As with any infinity natural transformation, there's higher order terms which count similar polygons obtained from a bunch of Lagrangians and counting now things with more, some inputs and one output. Okay, so and now we have an exact triangle of functors in the Fukaya category of the fiber. And I believe this lives mostly in unpublished work of Abu Zaid and Ganatra.
So half of this story is already written in this appendix of paper with Ivan Smith.
Okay.
But no.
Okay, so there's various partial references to this. Anyway, so we have an exact triangle here, which you can convince yourself at least, very naively at the level of this makes vague sense. Actually, no. If I look at cup little l and then cap that, right? So cap cup L, what it looks like is I take L, I transport it around to get cup L. On this side I have mu inverse of L, and then I cap that, so I get, of course, something that involves L and mu inverse of L. And the connecting map, I say in the cap functor, is exactly this section counting thing. So
actually, it is in this entire thing is in the paper.
Okay, so it's in the appendix of Evan Smith.
Yeah.
Okay, your paper. Yeah. Okay. So this can be found. And there's also another natural thing to do to look at in the other direction, in the total space. There's an adjunction in the opposite direction. I believe this whole thing is called a spherical functor or something like that. This is not my comfort zone, so I won't go there. But this is like one half of the story. And so now, if I want to recast what Mohammed and I do in this language, if I have a hypersurface in C star to Vn or a toric Fano, then we expect to have a commutative diagram of homogeneous mirror symmetry equivalences. Involving these cap-cap functors and monodromy action. This side. Now, here we have HMS for toric varieties, which says that this is the same thing as the derived category of V. And the calculation shows that the monodromy around the central fiber is mirror to tensoring by O of H, the defining line bundle of the hypersurface. Okay, this is basically contained in Hanlon's thesis. Now here we have functors which are inclusion and restriction. Well, this one is restriction to H, this one is inclusion into H, into V, sorry. And so now we expect to have a commutative diagram here. So the disclaimer is, in the very affine case, this is, checked for everything. In the case of toric varieties, so far we have clear compelling evidence for things that come from line bundles on V. Now, since those generate the derived category of V, and their restrictions usually generate here as well, I'm not going to be too worried about this working out. But we haven't completely checked the full HMS statement in the case of it.
Sorry,
Yes?
you said that okay, the restrictions of ambient line bundles generate with their
Yes, I think they should. Well, at least in the projective case, they will, because you will have ample bundles in there.
Does it mean that there should be some admissible Lagrangian in the mirror to H that it's a muscle surface surgery on the ones you have for mirror to a line bundle that is not?
Well, I mean, okay, for twisted complexes and idempotent summands and everything you need, okay? I'm not claiming that there's actually a single Lagrangian that does it. Okay. All right. And so basically the point now of the calculation stage of the thing, after you've made sure things are defined and consistent and so on, is that the natural transformations S from mu inverse to identity corresponds under this side of mirror symmetry to multiplication by the defining equation of L of H from tensor with O of minus H to identity. So basically things match with each other. And so in this language, what we've calculated when we checked things for U-shaped Lagrangians is that hom between cup L and cup L prime by adjunction is the same as hom from L to cup L prime. And now this is going to be the cone of, I'll use that on the next line. Using the exact triangle, this is the cone of a map from hom L mu inverse L prime to hom L prime in the fiber given by S, which is the same as multiplication by F when you calculate it. Okay? All right. So now you understand what happens in algebraic geometry. This is, maybe I should write it here. This is equivalent to, in algebraic geometry, calculating hom, or rather X, from two restrictions of sheaves on the ambient space is cone of hom E prime tensor O of minus H to hom E prime just by basically resolving the restriction of E prime by E prime tensor O of minus H going to E prime. Okay. All right. Okay, so having talked about functors, anyway, so now there's a very nice structural picture, but I'm just going to leave this alone. And now I want to move back to the main thrust of where I want to go, which is, are there ways to simplify this story to avoid talking about this Landau-Ginzburg model? Okay, and so, sorry, questions about this first, because this is a natural place to stop.
So what about assumptions on V again?
So V is, let's say, toric Fano. This also would work for abelian varieties. That's then Canizzo's thesis instead. And H is a hypersurface, or rather a family of hypersurfaces degenerating to a tropical limit. And the construction of mirrors is, as explained yesterday. And sorry, I should say, there's a similar story for complete intersections, just I don't want to bother stating it, because now you have multi-resolution, whatever, you have the causal resolution of the complete intersection. And I need a higher dimensional blackboard for that. Okay. All right. So ways to avoid the Fukaya category of y double. Having spent a large amount of time and effort thinking about this, can I try to get rid of it? So I'm going to talk about 3 different ideas. And first of all, I will just sketch quickly because I want to focus, well, maybe not at the end of today, but then all of tomorrow. The last lecture will be about the last of those. So first idea is this idea of Knower periodicity. So, namely, if it happens, if somehow Y ends up being the total space of a line bundle, in fact, the canonical bundle over Z, a toric variety, okay, and the superpotential ends up being something that's linear in the fiber coordinate times a section of the anti-canonical over Z. Okay, so for example, remember we saw last time for the pants, this is C cubed minus Z1, Z2, Z3, and then, so the claim is we hope to reduce to, let's call that D0, which is the 0 set of sigma inside C. So here this would be Z1, Z2 equals 0 inside C squared. So just this singular nodal curve. The other example we saw yesterday was with a 3-punctured torus, which was going to give us O of minus 3 over P2 with, I don't really want to write the, well, 2, and then this gave us the 3 nodal, the union of coordinate axes in P2 as the mirror. And discuss briefly how when you compactify this inside the toric variety, then you end up with a smoothing of this nodal curve. Okay. So the question you can ask is there a way to do mirror symmetry using directly this D0? And so if you were doing the algebraic side on D0, the answer is of course yes. dB_co of this kind of thing is perfectly fine, and you don't need to worry too much about anything. On this side, the question is how does one define the Fukaya category of such a thing? And so there's a proposal for that, in fact, which is, okay, so consider D0 as a singular fiber in an anti-canonical pencil on Z. Okay, so divisors, let's give names to them. So T on Z. And so then, so when you have this setup, okay, so the simplest thing to imagine is that you're in the affine case like this, because then there's no base points, but even if you have base points, you can do it. So you can think of a pencil as being birational map to P1. So in particular, locally you have in this family, you have something which has this D0, and nearby you have D sub T, the smoothings. And this is all in the world where we want to do symplectic geometry. And remember, we just spent some time discussing monodromy and natural transformations from section counting. So let's do the same thing here. You want to think about, so now you have the monodromy around 0 again, and you have the section counting natural transformation. The monodromy around 0 of this pencil acts on the Fukaya category of D0. And there's again a natural transformation call it S again, from either mu inverse to identity or identity to mu. It depends on how you normalize it, whether this leg or this leg is the input. And all right. And so the claim is now it makes sense to define the Wrap-Fukaya category. Maybe I should have said Wrapped. The Wrap-Fukaya category of D0. Sorry, this is a problem. Right, the monodromy acts on the Fukaya category of a smooth fiber. Okay, this one has not been defined yet, and now the claim is define this one by localizing. At S. Okay, so this is a natural thing to do from various perspectives, but one that's maybe particularly compelling is that in this diagram here of things, localizing at S amounts to localizing at the defining equation of the hypersurface, and therefore it amounts to restriction to the complement of the hypersurface. And there's grounds to notice when you apply the whole setup again to the complement of a hypersurface viewed as a hypersurface in one dimension higher, that in fact, basically you expect the central fiber of the Landau-Ginzburg model to be the mirror to the complement of the hypersurface. So this does exactly the right thing in our class of examples. Okay. And so now you can check indeed on those examples. Well, these are just nodes, so that's particularly easy. I'm going to go here actually, but it was exciting. So we expect, a Knauer periodicity type result. Which is that this localization is equivalent to the fiber-wise Wrap-Fukaya category of the total space of a line bundle with that superpotential we were considering. This is something. And so in this level of generality, I don't think I know how to prove that. But first observation is this is manifestly true in the nodal examples that we have over there. Right, so in the nodal case, you know that say for example, look at the mirror of a pair of pants. The smooth fiber nearby is just a cylinder. Right? If this is like Z1, Z2 equals 0, this is Z1, Z2 equals T, then C squared. We know the Fukaya category of this. Okay? The category of the cylinder is equivalent to dB of C star. The vanishing cycle for this nodal generation is just a loop here, which is mirror to skyscraper of a point. And the natural transformation that you get, so monodromy is the Dane twist, which is just identity in this case. But the natural transformation is multiplication by 1 plus x on this. So, okay, and so this tells me that now if I localize at 1 plus x, I will get the derived category of C star minus, well, I remove a point at minus 1, which is exactly the path. Okay? So indeed, in this baby example, the derived category of H is obtained. Sorry, the derived category of H is obtained by exactly the same localization that we want to do here. You can do the same as an exercise on the elliptic curve that works very well as well. And there's a more general result about this, which unfortunately so far is only stated in the affine case because of technical reasons. So this is the work in progress of my student Maxime Jeffs. Says the following thing. Let's say that we have a smooth affine variety. It's not toric anymore. We have a regular function on it with 0 critical level. So this is going to be a singular hypersurface. There are some technical assumptions on the singularity which are very mild. I Actually, I do not know a counterexample. For me, we haven't thought. So I will omit them for lack of. And then define the Fukaya category of a singular hypersurface by, again, looking at the other levels and localizing at the natural transformation as above. Then this embeds fully faithfully the expectant equivalence into the Fukaya category of the product of Z with C. Line bundle is trivial now. Let's call this coordinate U with superpotential U times F. And so this should work much more generally. The assumption that we're in the affine setting and so on, besides avoiding issues with pencils versus vibrations, also makes sure that you can use, you're in the exact setting, and then you can use the technology of sectors. And the actual proof that Maxime is writing up right now is in the language of Genatra Pardon Chen des Liogen sectors.
Can I ask, so
Yes.
is there any hope to prove that this is independent of the, but this depends only on the zero fiber?
Is there any hope to prove this only depends on the zero fiber? So I don't know how I feel about
Seems
that.
theoretical, for
Yes.
example.
I don't know whether I believe for sure that. I mean, yes, I think there's supposed to be an algebraic result that says about germs of hypersurface singularities or something.
Okay.
So there are cases where basically the zero fiber determines its formal neighborhood, I think, and therefore something. Outside of that, I'm not sure if I even believe that it should be true apart from such phenomena.
There's something like it's after idempotent completion.
Yes, probably.
No, but that's on the-
No, that's on the other
on the
side.
B side.
That's on the B side.
Okay.
Yeah, I mean, here you're actually trying to build an actual neighborhood, right? You're trying to do symplectic geometry in the neighborhood of D0. But I mean, apart from some results like that, that kind of tell you the ambient space is locally unique, I do not know how one would actually prove independence.
Other than by one of the other methods you're going to propose.
No, because I'm not sure I can claim independence. I mean, I'm not sure I know that things. Anyway, yeah. It's actually a good question. I don't really know. Well, it is the end of my written notes. I need to turn to technology because. Okay. Very good. So next is tropical Lagrangians. And this is really like just an interlude on the way to the next thing I want to explain. But I think it helps motivate the construction that I will focus on tomorrow. So observe in general, so far we've done this calculation by saying, okay, so I'm still returning to the total space, but now we will try to focus on the fiber of W0, which means C star to the n equipped with W sub v. Okay, so remember the main calculation scheme I was explaining before is if I try to compare two U-shaped Lagrangians, then I get this mapping code, but I also explained to you just a moment ago that I can think of this by adjunction as Homs in the fiber F. Let's call that F, between one Lagrangian in the fiber and cap cup of the other one. Okay, and cap cup you should think of as being really the resolution of the restriction re-included. This is I lower star, I upper star, E prime, under mirror symmetry. Okay. But so now you can ask, well, if I take, say, a line bundle, I restrict it and I re-include it, then of course I can think of that as a mapping cone of two line bundles as I did before, but there's a more direct thing to do, which is get a sheaf supported on H. Okay, this is a sheaf on V supported on H. And so we want to understand maybe, is there a direct way, under mirror symmetry for toric varieties, to understand mirrors of sheaves supported on the hypersurface H. And this is the talk where I get to list my recent grad students. So this is where the work of Jeff Higgs, construction of tropical Lagrangians, exactly gives mirrors to things like O sub H and, in general, line bundles respect H. Okay, so how does that work? Well, and you'll see, so there's other constructions of such tropical Lagrangians, like Mihalkin has one, Matesi has one, I think this is pretty much Nick Sheridan, I think, with Ivan maybe, has one, I forgot. Anyway, there's a bunch of these constructions appeared at the same time last year, but this one does exactly what I want, so that's exactly why I will explain this one. So here's a short 5-minute version of Jeff Higgs' thesis. The mirror to O sub V, structure sheaf of rhetoric variety, is the zero section of the log map from C star to the n to Rn. This is just a fancy name for R plus to the n. Okay, this is the guy I've been calling L0 all along. So, and this is admissible for any monomial admissibility condition. Now, the mirror to O sub V of minus H, as first seen by Mohammed and then slightly reformulated by Andrew Hanlon, is the admissible Lagrangian section. I will call that now L of minus H inside C star to the n, obtained by smoothing the graph of d phi. Remember, so phi was the tropicalization of f, the defining equation, back from lecture 1. So where does this live? So remember, phi equals tropicalization of f, for example, was a max of a bunch of linear functions determined by the equation. This is a piecewise linear function from Rn to R with integer slopes everywhere. So if I look at the graph of the differential of a function from Rn to n to R, that lives in the cotangent of Rn, and I will periodize by the integer lattice. And this is, of course, by the exponential map, the same thing as C star to the n. And there's a slight cheating amount here, which is that if you use the standard Kähler form on C star to the n, then the log map is the moment map. Otherwise, this should actually be happening in the moment map picture, not in the log map picture. And okay, so what do I mean by smoothing? Well, this is a piecewise linear function, so you would just see a bunch of locally constant slabs, and these actually are all integer slope. So in fact, it would everywhere agree with the zero section. You would have lost all the fun. The right thing to do, of course, is to first smooth and then calibrate. So what I mean is, so for example, for the pants, so phi was going to be max of 0, C1, C2. So look at the piecewise linear function given by 0, C1, and C2 on R squared. And then I smooth it so that the profile here, instead of being an abrupt wedge, instead is a rounded thing. And then I take the graph of D of that. So, of course, when I take dx1, this is 0 mod the integer lattice. But from here to here, the slope has continuously increased by 2 pi. So, well, not 2 pi because I do with z, so by 1. I mean, 2 pi equals 1 today, okay? And so basically I've gone once around the argument torus, okay? So that in fact, if I try to draw a cross section in this direction, I start at the 0 section, I end at the 0 section, but I twist by 1 turn in between. Times something trivial in that, times R plus in that factor, same thing for the other legs, and in the middle you have to figure out what, manifestly there's something. What it is hard to picture. Okay. So now that you have the mirrors to these two line bundles, you can try to cone them. How do you cone them? Okay, so we have two Lagrangians, and they actually overlap away from the tropical hypersurface. So the region where these two Lagrangians, this Lagrangian does not agree with the zero section, can be made to be just a small neighborhood. So in fact, something that's amoeba-shaped here. Okay, and so now the next thing to realize is that there's a Lagrangian surgery operation. So Lagrangian surgery usually refers to you have transversely intersecting Lagrangians and you smooth the intersection. But there's a version of it for this setup, which is more like a symmetric difference operation. For Lagrangians which overlap on open subsets and then branch off smoothly from each other. And so what it does, in this model picture of a cross-section, is it replaces these two Lagrangians with something that follows them in the regions where they're different, but then near the corner, you kind of round things like this. Okay, so this is L sub H, which maybe L upper H, which is obtained by surgery of L of minus H with L0. Okay. And so this gives you a mechanism to understand Lagrangians that are mirror to. So this one gives you the mirror to the structure sheaf of H, and just by twisting in the argument directions, you can get overlying bundles. Okay. So Jeff Higgs shows these tropical Lagrangians so they're in C star to the n, and they're automatically admissible with respect to the superpotential we want, are mirrors to line bundles on H. Okay, so there's a slight warning sign here, which is that we need to adjust surgery parameters with care, or to adjust the defining equation of H with care, because if you don't do the right construction exactly, then you will end up with you will still manifestly end up with a mapping cone from O of minus H to O, but what you're coning might not be exactly the defining equation of H. It might be a small deformation in fact. So you need there's a bit of hidden stuff hidden there. All right. So now why this relates to what I want to continue with is that, moreover, there's a surgery cobordism. And so this means, so we can redraw these like cup Lagrangians in a way that makes cap cup L manifestly a tropical Lagrangian in C star to V. So what does the picture look like? The picture looks like, okay, so we've started, let's do the case of a pair of these, for this is going to be hopeless very soon. So we start with R plus squared, which is L0 inside C star squared, and we transported it around the origin. That was what we were interested in doing. So now, instead of leaving these legs alone, I'm going to actually make them intersect. And because of the monodromy around the origin being exactly this bending across the amoeba of H, what you end up with here, in this fiber here, is in fact a copy of L0 and a copy of L minus H, just from the action of the monodromy on what's happening in the fiber. Now, this is not where you want to do the surgery yet. This goes in the wrong direction. Instead, let them cross. You get an immersed Lagrangian. Then bring them back together again. And now the claim is here there exists a Lagrangian cobordism between L0, L minus H, and now, I don't know how to draw that, L upper H. This one has parentheses. Which, sorry, in this case is a pair of pants. It's a Lagrangian pair of pants inside C star squared, whose log map projection looks like what you expect. I mean, in some sense, this particular one you could probably get more cheaply by hyperkähler rotation of a pair of pants in C star squared. But that's not how we want to play this. Okay, so this gives an admissible immersed Lagrangian in y, w. It is not tautologically unobstructed because there's teardrops here and there's teardrops here, but they exactly cancel out if the cone you do here matches the defining equation that's the natural transformation here. So what this does is it makes it manifest that you should think of this tropical Lagrangian as the vanishing cycle for something that wants to be like a thimble. So,
Sorry,
yes.
let me finish.
Let me just finish the sentence. So the tropical Lagrangian so H is a vanishing cycle in the smooth fiber F for the admissible Lagrangian. Yes?
You have 3 minutes. Do you want to finish talking and asking questions?
Sure. Okay. Let me. Yes. So, okay. And so you can ask actually, is there a genuine thimble in the sense of a Lagrangian that fibers just over a straight arc from the origin to over there? And the only case that I know of where the structure sheaf is able to do that is if you just do the mirror to instead the point inside C star, which is kind of a bit of a let down, but this is mirror, this is 1 dimension less than the pair of pants. This is C squared minus Z1, Z2. This is a Lefschetz fibration. And then the crazy construction we've been doing involved parallel transporting R plus, so the whole arc running through the cylinder along a U shape around the origin. And okay, so you get this Lagrangian, which kind of goes all around. And what I'm telling you is by Jeff Hicks' trick, you can instead replace it with something that will do that. Now, in this case, the surgery between this and that is just the usual vanishing cycle. Right? This is exactly the picture that's still here. This looks like on a cylinder, this looks like 2 straight arcs coning to form a loop. And indeed, this is isomorphic to the well-known Lefschetz thimble, which is the thing that parallel transports from the singularity to give me a Lagrangian disk. So in the case of a pair of pants, we can also do that for skyscraper sheaves of pants. Okay, so for the case of the pants and the other examples more generally, the critical locus looks like this. It's the union of the 3 coordinate axes in C cubed. And one thing I can do, this is Morse bot away from the origin. So I can take an S1 inside of one of these coordinate axes and then parallel transport it. And over each point, there's a thimble which is a 2 disk. So in fact, this transports to a solid torus. Okay, over the line from 0 to infinity. And these things have a name. These are sometimes called the Agenagich-Waffa Lagrangians, because they come up in their work on. And they correspond to skyscraper sheaves of points on the pair of pants in this example. So now you can ask, well, okay, what point and how does it work? Well, there's a coordinate here. This is like a product torus, which corresponds to a point corresponds, this product torus with a local system corresponds to a skyscraper sheaf of a point in the fiber mirror C star squared. And that point, of course, should be on the pair of pants, because otherwise, I mean, you know, that's our statement that looking at the boundary cap functor corresponds to push forward by inclusion. So this point has to be on the pair of pants. So in fact, it's in H inside C star squared. And you can ask, well, this is strange because, you know, remember these coordinates correspond to moment map position plus holonomy of a local system. One of the two factors of this torus actually bounds a disk in here. It's the factor that collapses to a point. So any local system on the solid torus would have to have trivial holonomy on this circle, which would mean that one coordinate here would have to be actually equal to -1. Minus because of spin structure things. Classically, for example, x1 equals -1 when valuation of x2 is positive is equal to the area of this thing. Okay? But, well, you see, this notion of area tells me there's a problem. There's a holomorphic disk here, and so this Lagrangian is obstructed. I need to equip it with a bounding cochain. And this has the effect of correcting the holonomy at infinity in practice. You can think of a bounding cochain as curving the local system. At infinity, the holonomy x2 is whatever it is, but x1 gets deformed to -1 minus x2, which is exactly where your point should be to be on the pair of pants. I think people like Melissa Liu have a much nicer way of explaining that. So anyway, so basically, skyscrapers of points can be understood as thimbles. For O, there is no such description. There's only this like weird, you know, twisty loopy thing. But basically, there is an almost metal description that says that O would want to be built as a thimble out of this triline graph. Problem is, if you do parallel transport here, you can only build a piecewise smooth Lagrangian, and I do not know of any way of smoothing this. I'm sure there's one, but I don't know it. So next time we'll talk about what happens if we just postulate that we can work with these pictures and do Floer theory directly here. And I think this is where I should stop for today. Thank you.